Okay, class, in the last video we ended with saltatory conduction, and I've actually included a video of someone else giving an explanation of saltatory conduction also that you'll see in the D2L. Okay, so we talked about that. We talked primarily about that myelin did this saltatory conduction, and we were showing how its speed was to speed up nerve conduction. So we have certain conditions that are demyelinating conditions, like multiple sclerosis or something called Guillain-Barré. In this case, multiple sclerosis is an autoimmune disease. Won't say much on it, but obviously what does that mean? It would slow down nerve conduction with those with multiple sclerosis, okay, particularly in the spinal cord area. We go further, then we mentioned that diameter and myelination were the key things that would speed up nerve conduction. And we said some neurons are fast and some are slow and so forth and so on. So here is a nerve fiber classification. We have what we call group A fibers, group B fibers, group C. Now these would be axons. The group A are the big boys. They're the large ones, large diameter and myelinated. Remember somatic sensory when I was telling you about getting scratched on the skin and so forth, and somatic motor. Our skeletal muscles need to get real quick on their movements. Somatic motor. Group B, intermediate, lightly myelinated. These are some fibers in the autonomic nervous system. We haven't done that yet, but these are what we call preganglionic fibers. We'll talk on that though later. And then group C are also in the autonomic. Remember, autonomic goes to smooth muscle. That's real slow stuff. That's real slow stuff. So, like in your bladder, your intestine. So that's the group C. Small diameter, no myelin. So really the slower stuff is in the autonomic and the fast stuff is in the somatic, to say it another way. Okay, let's go a little further then. Now I'm going to PowerPoint 3. Nerve tissue 3. Okay, and this is where we are. So we go into nerve tissue 3. And I'm going to make that small. Okay. Now, again, we're back to that electrophysiology. We did the synapse. We discussed that. We discussed the presynaptic and this. We talked about synapses. Now, we haven't, okay, here's some examples of synapses. This would be what we call a neuronal. Okay. Neuron to neuron. Now, this is what I want you to understand. These types of synapses here are going to be what we call neuronal. Okay, neuronal. Neuron to neuron. See, we had, you know, before we talked about neuromuscular when we did the muscle. Okay, the possibility. An axodendritic, that means the axon of one going to the dendrite of the other, and that's generally the most common. The other would be the axon of the pre going to the cell body of the other one. That's like the second most common. Less common, an axon to an axon, rare. A dendrite to dendrite, rare. Dendrosomatic, rare. So these I'm not going to even get into. Okay, but the most common is the axon to dendrite, axon of one to dendrite of another one. Axosomatic, axon of one to cell body. So if this was the second guy in line, an axon would be coming down from a pre and touching one of the dendrites. To say it again, if this was the second guy, the second neuron, and it's an axosomatic, then the axon would the first one would come and synapse directly on the cell body of the other. Okay. The rarer type would be the axon of one synapsing directly on the axon of the other. But that is the third most common though. So most common, axon of the first one to dendrite of the other. Second most common, axon of the first one to cell body of the other, axosomatic. Third most common, axon to axon. These others are almost virtually almost non-existent. All right, so we go a little further. So they're showing it here, you know, okay. Axosomatic, see, axon of one to cell body of the other. Axodendritic, axon of one to dendrite of the other. Okay. Axoaxonic, axon of one to axon of the other. Okay, just to show you. All right, electrical synapses, we talked about that. That's where you have gap junctions. And basically what happens is the action potentials can travel through the gap junctions to the next entity. These neurons are electrically coupled. Okay? Embryonic nervous tissue has it. Some brain regions, but very few. Most use chemical synapses. Okay? Chemical synapses, we talked about that heavily. Go back to my electrophysics. That's where you had the presynaptic, release the neurotransmitter, had the cleft, talked about all of that. I'm not going to get into that. Information. Here would be what we already did. All of this. Graded potential, talked about that in electrophysiology. So just go back and look at that. That's all you have to do in my electrophysics. We talked about termination of neurotransmitter. One was by enzymes in the postsynaptic breaking it down, like acetylcholine was broken down by acetylcholinesterase. Reuptake by the axon terminal or by astrocytes around it. And then remember, between that synapse is a fluid pool. So in other words, fluid would just wash it away. So one thing would be break it down, because the postsynaptic would make enzymes and break it down, like acetylcholine is broken down to acetate plus choline. The others just suck the stuff back up and take it back to the cell body, and the others the wash away. So that's essentially how you would get rid of termination of neurotransmitter substance. Because if you kept it forever, how would you ever turn off the second neuron? Okay. Synaptic delay. See, with the electrical coupling we talked about, where the action potentials went directly from one through the other through gap junctions, there's no synaptic delay. But with chemical synapses, which are the most common, there is. Neurotransmitter must be released, diffuse across, synaptic delay, and so forth. Now let me kind of give you an example of why this synaptic delay is pretty good. Okay, you know, on the radio, for example, there's a little delay on the radio when somebody says something to when it gets out in the public. A little delay. Suppose somebody said something that they shouldn't say, just one word or two words, and they're like, oops. See, with that, if there was no delay, it would be out there. Be no bleeping or nothing. Be no bleeping or nothing. But with the delay, it allows that. So let's say this. Let's say you're looking at somebody and you say they got a suit on. You say, oh God, that's an ugly suit. See, what would happen in your brain, if you had electrical coupling with no delay, you would have already said it before the minute you thought it. Think about it. You would have said it the minute you thought it. No social skills would occur. But with synaptic delay, you have a moment of delay, plus you have so many inputs coming into these synapses to kind of block them. So that's this chemical is slower, but is better. If all of our neurons were hooked together by electrical synapses, muscles and neurons, we'd be about 10 to 12 times faster. We would be doing things considerably faster, but we would have no rationalization, no socialization either, because we'd be saying and doing things we shouldn't, and it would occur at a very fast rate. So that's kind of looking at it in a generic way. But we do have a synaptic delay when you're dealing with chemical synapses. Okay, let's go further. Okay, postsynaptic potentials, we already talked about that. EPSP, IPSP, that's in neurophysics. Go back. Okay, so we already talked about all of that particular stuff, and you can do that yourself. Now, if you read my electrophysics and then do this, again, you'll get a good understanding of this. There's no point in being redundant on these things. Okay. Now, when we're talking about integration, we get into what we call the EPSP and the IPSP, okay? And then we get into what we call temporal and spatial summation. Temporal and spatial summation. So I'm going to start another video on this integration summation.